Okay, so we've got a solution here for our damped driven system, and we've got a term that comes about from the solution of the homogeneous equation that takes care of initial conditions, and another part that takes care of the driving. This functional form, though, is full of imaginary numbers, and our initial conditions and driving force are going to be real. So how do we get rid of all the imaginary parts? I thought it was worth going through this. Let's suppose we have a system where we've got a driving force that is given by this real function here, b times cosine omega t, and initial position of 0, initial velocity of 1, with units of position and velocity of your choice. So first we're going to find the complementary function, that is the solution to the homogeneous equation, and just ignore this part for the time being. And we're going to take the real parts of all the complex bits, because of course that's what we always mean. When we write down these complex valued functions, we mean implicitly that we take the real part to find what is actually happening physically. So we say that at time equal to 0, we have position equal to 0, and we take the real part of this function here at time equal to 0, giving us one equation for the constants c and delta. Then we take the derivative of this function and set time equal to 0 and set the value equal to 1, giving us the real part of all of this must be equal to 1. And so we have a second equation here. We can solve these two simultaneous equations, and we find that delta must be pi on 2 and c is equal to -1 on omega dashed. So now we have solution for the undriven part of our equation. And we can see it's fully real valued because we can take the real part of all of this here and we find a function that just depends on the sign of omega dashed, a damping exponential out the front and some constant out the front. Now, if I'd chosen more complicated initial conditions, then this would have a sine component and a cosine component, both going with the frequency omega dashed. So onwards to the driven part of this equation. This is kind of easier. We don't have to solve any simultaneous equations. We just, inverted commas, have to manipulate complex numbers, which, you can decide whether that's easier or not. A note on the driving function. So the driving function here I've taken as b times cosine omega t. Now, if you look back at the videos or the notes, you'll see that when we set up the solution to the driven part, we assumed a driving force of f0 times e to the I omega t. Now, of course, what we mean by that is the real part of f0 times e to the I omega t, which is f0 times cosine omega t. So all along we've been driving with a cosine function. What we're going to do now, though, is explicitly calculate the real part of the solution that we found. So we were driving with the real part of b e to the I omega t, our force here is b, and this bit in the brackets here was the solution we found, and now we're going to find the real part of this, which will give us the real valued function for our real valued driving force. Now we'll expand the complex exponential into its sine and cosine components, and then find the real part. So first of all, we expand e to the I omega t into cosine omega t plus I sine omega t. And now this part in brackets, to find the real part, we add that to its complex conjugate and then divide by 2. So here is this function in brackets, and then we're adding the complex conjugates. I've just inverted the sign of everything with an I and multiplied by a factor of a half. We can collect all the sine and cosine components, and lots of things cancel out. And we find that the function xp is now given by this real valued function here, dependent on sine and cosine components of omega t. This is actually kind of a useful form to have the function in. You can see that when omega is equal to omega naught, so when we're driving at this undamped resonant frequency omega naught, then the cosine component goes away, and the response, the position, is a sine function. So you can see, directly looking at this equation, that the phase of the position is now pi on 2 with respect to the drive, because cosine and sine are different by a factor of pi on 2 in phase. Another thing to realize is that if we've set the solution up for anything that is sinusoidal, because we solved it with e to the I omega t, and that represents sine and cosine functions. Here we've put an explicit real valued cosine function in, but if you wanted to do it with a different sinusoid, then what you do is just add a phase shift to this omega t. So you could add a phase here, so omega t plus some phase theta. Now you can just carry this this phase of theta through every time where you see an I omega t. So you have a plus theta here, and here, and here, and here, and until finally all you've done is shifted the phase of everything down here by a factor of by phase of theta. So hopefully this demonstrates that although everything written here is got all these nasty looking imaginary numbers in it, in fact this is just a kind of a compact way of representing these kind of even nastier functions that we can write out explicitly in terms of sine and cosine functions.